Alright, boys and girls, welcome to our third video lesson in Chapter 2, our lesson on Section 2-4 on complex numbers. Okay, here we go. First of all, take a few minutes here and solve for x in these seven quick little equations here. Hopefully you can do this pretty quickly and in your head, but stop the tape and give it a go. Alrighty. Okay, as we're looking here, the first one, be careful, it's not 3, I tricked you, it's 81. The square root of 81 is positive 9. Notice that when we take the square root of a positive number, our result is the square root of that number, which is, yes, both plus or minus, but by definition, a radical of a square root is always the positive answer, so it's 9. So our x is 81. So we're looking at the second problem right now. There is no solution because the square root of x is equal to negative 9. Well, by definition, yes, the square root of 81 is negative 9. It's also positive 9, but the radical, just the radical piece of it, it must be positive, so there's no answer here. The square root of 9 now is 3, so that's 3. Notice it's positive 3. Radical 9 is 3. However, the square root of 9 is both positive and negative 3, but radical 9 is 3. The square root of a negative, again, does not exist, okay? And for a different reason, you can't take the square root of a negative number because positive times positive is positive, and negative times negative is also positive. So the square root of a negative does not exist in the real number system. All right, John Cody. Example 5 here, the third root now. The third root of 27 is 3 because 3 to the third power is 27. The third root of x is equal to negative 3. Well, yes, we can take the third root of a negative number and have a negative answer because it's an odd root. So therefore, this answer is negative 27. But notice when we go back to an even root, the fourth root of a negative does not exist. Sorry about this. Here, okay, so the square root or an even root, in this case the fourth root of a negative, does not exist. However, the fourth root of positive 81 would be 3. This is a pattern now. We're going to talk about the imaginary numbers. Okay, the imaginary numbers, by definition, I is equal to the square root of negative 1. Okay, any number raised to the 0 is 1. So I to the 0 is positive 1. I to the first, we just said, is the square root of negative 1, which is equal to I, of course. Any number to the first power is itself. The square root of our I squared is equal to negative 1 because the square root, let me write here. The square root of negative 1, so 1, times the square root of negative 1 is going to equal negative 1. So I squared is equal to negative 1. I to the third is going to be I squared times I. I squared, of course, is negative 1, so negative 1 times I is negative I. Okay? I to the fourth is I squared times I squared. Well, I squared times I squared is neg 1 times neg 1, which, of course, is positive 1. When we get back to I to the fifth, we have I to the fourth times I. Well, that's 1. 1 times I is I, which is the square root of negative 1. I to the sixth is negative 1. I to the seventh is negative I. I to the eighth, again, is 1. Notice we have a pattern of I, negative 1, negative I, 1, I, negative 1, negative I, 1. I to the ninth would be, once again now, I. Okay, so we can now simping. I to the 14th, we just got to take out the biggest multiple of 4. I to the 14th is equal to I to the 12th times I squared. Well, I to the 12th is 1 because it's a multiple of 4. 12 is a multiple of 4. So this is just 1. So this is I squared, which is negative 1. I to the 44th is I to the 44th. 44 is a multiple of 4, so this equals 1. I to the 143rd is I to the 140. Why do I choose 140? Because it's a multiple of 4 times I to the 3rd. Well, this is 1, so this is I is equal to I to the 3rd, which of course equals negative I from that little pattern. You guys try these too. Stop the tape and go ahead. Okay, I to the 70th is I to the 68th times I squared. I to the 68 is 1. I squared is negative 1, so the answer is negative 1. And I to the 701st, well, the biggest multiple of 4 in 701 is 700. So this is I to the 700 times I to the 1st. This, of course, is just 1. This is I to the 1st. I lost my 1 there. So that is equal to I. Okay, let's just review for a minute. A complex number is, in standard form, is A plus BI. A is called the real part or the real component, and the BI part is the imaginary part or the imaginary component. Don't forget, we can do work with the imaginary numbers and complex numbers on our graphing utility, on our graphing calc. Just change your mode from the real number mode to A plus BI mode. And in fact, you can keep it there because everything we do in A plus BI mode, you can also do in real number mode as well. The complex conjugate, we already know conjugates. The conjugate, for example, of A plus B, the conjugate is A minus B. The conjugate of A minus B is A plus B. And those things are great because when I FOIL them out, when I multiply them, the middle terms disappear and I end up with a difference of squares. Okay, so the conjugate of A plus BI is A minus BI. If I multiply them, I'm going to get A squared minus BI quantity squared. Okay, so as we look at this right here, let's just write the conjugates. I'll do that in red. Do that in red. The conjugate of this is 6 minus 2i. You guys are probably way ahead of me. This is 5 plus I. The conjugate of root 3 minus 2i is root 3 plus 2i. And the conjugate of 0 minus 3i, remember there's a 0 there, 0 minus 3i is 0 plus 3i, or just plain old 3i. If I multiply these numbers by their conjugates, the first one is going to be, I'll do that in blue so we can see, 36, 6 squared, minus 2i squared, which is 4i squared. 2i quantity squared is 4i squared, right? So that being said now, 36 minus 4i squared, well, I squared is negative 1. So 36 minus negative 4 is 36 plus 4, which equals 38. 5 minus I times 5 plus I is going to be 5 squared, 25, minus I squared, which of course is negative 1. 25 minus negative 1 is 25 plus 1, which is 26. Root 3 minus 2i times root 3 plus 2i is root 3 squared, which is 3, minus 2i squared, which is 4i squared, which now becomes 4 times negative 1, which is negative 4. So 3 minus 4 is 7. 0 plus 3i times 0 minus 3i is 0 squared, minus 9i squared. Well, negative 9i squared is positive 9 because it's negative 9. Okay, make sure you get these into your notes. The fundamental theorem of algebra says any polynomial function to the power of n is going to have n number of roots in the complex number system. Some of those roots might be duplicates. Some of those roots might be imaginary roots, but there will always be the same number of roots as in the power of n. Another very important theorem is the complex conjugate theorem, which says if a plus bi is a root of a polynomial, then a minus bi is also a root. In other words, the complex roots always come in pairs, the root and its conjugate. This is very important. So if I say to you, square root of negative 9, simp, we now know the square root of negative 9 does exist in complex numbers. The square root of negative 9 is 3, oh, I need my pen, is 3i. Okay? When I do a problem like this and I'm multiplying two radicals of negatives, two, imaginary square roots, the trick we always learned before was to multiply inside the radicals first. So this is going to be radical negative 9 times times negative 9, which is radical 81, which equals 9. This, unfortunately, is not the correct answer. When we do this, we need to say, okay, we just did this up here. Radical negative 9 is 3i. Radical negative 9 is 3i. 3i times 3i is 9i squared, which then becomes negative 9. And so when we're multiplying two radicals with negatives, we end up with a negative answer, not positive. So just be careful of that. Muy importante. Let's just do some algebra 2. This is all review. We're going to FOIL here. So 8 times 5 is 40. 8 times negative 3i is minus 24i. Negative 2i times 5 is negative 10i. And negative 2i times negative 3i is plus 6i squared. I can combine my i's. I get negative 34i. 6i squared becomes minus 6, because I squared is negative 1. 40 minus 6 is 34. So I have 34 minus 34i. Looking at this guy right here, these look like conjugates. Let's make sure. 9 times 9 is 81. 9 times 3i is positive 27i. Negative 3i times 9 is minus 27i. And negative 3i times positive 3i is minus 9i squared. Okay, again, we see that my middle terms will cancel. Negative 9i squared is negative 1, so this becomes positive 9. 81 plus 9 is 90. When we have an I in the denominator of a fraction, an I is in essence a radical, so we need to rationalize. So we're going to do what we did before with radicals. We're going to multiply both top and bottom by I. Up top now I have negative 3i over 7i squared, which is negative 7. Because 7i squared is negative 1. My negatives are going to cancel, and I have 3i over 7. 12 over 1 minus 2i. This time I just can't multiply by I or by 2i. I need to multiply by the conjugate, both top and bottom. So I have 1 plus 2i. 1 plus 2i, because the conjugate of 1 minus 2i is 1 plus 2i. Up top, I'm going to have now 12 plus 24i. On the bottom, I'm going to have 1 squared. I'll do this over here. 1 squared minus 4i squared. Well, 4i squared is negative 4. So that becomes plus 4. So I have 1 squared, 1. 1 plus 4 is 5. My final answer is that, because that's not simplifiable. 12 plus 24i all over 5. Okay, let's add some complex fractions here. First, I'm going to get a common denominator, which is 3 plus I times 3 minus I. So on the left side, I'm going to multiply by 3 minus I, both top and bottom. On the right side, I'm going to multiply by 3 plus I, both top and bottom. Okay. Now, on the left side up top, I'm going to distribute that 2i, so I'm going to have 6i minus 2i squared. So I got 6i minus 2i squared plus, this is all up top still, on the right side I'm going to distribute that 5, so I'm going to get 15 plus 5i. On the bottom I have 3 minus I times 3 plus I, which of course we know is 3 squared, which is 9, minus I squared. Well, I squared is negative 1, so that's 9 plus 1, which of course equals 10. Okay, up top I'm going to do some simping. I got negative 2i squared, which is positive 2. So I have positive 2 plus 15, which is 17. 6i plus 5i plus 11i, all over 9 plus 1, which is 10. Couple more here. 5i squared plus 4i to the third. Let's simp. Okay, this is negative 5 times I squared, which is negative 1, plus 4 times I to the third, which is negative I. Okay, this looks like 5 minus 4i. And last but not least, if I want to write a complex number, if I want to graph a complex number, okay, we did this in chapter 6 for the level 1 kids. Okay, this thing right here, this is my real number line right here. This is my imaginary number line right here. So if we think about x, y coordinates, okay, this is my x and this is my y. Well, now my x are my real numbers and my y are my imaginary numbers. So this, as an ordered pair, would be negative 1 comma negative 2. So if I wanted to state this complex number in standard form, this is going to be negative 1 minus 2i, where these are my real numbers and these are my imaginary numbers. Alrighty, have a great day.